idea of higher order derivatives. So we've already started learning about the first derivative and using the derivative rules like the product rule, the quotient rule, the chain rule, as well as the power rule. But I want to introduce the idea next that we can actually continue to take derivatives if that first derivative is differentiable itself. So let's review a couple pieces of notation. So the derivative y prime or dy over dx would be our first derivative of y with respect to x, whether we use the prime or the operator notation. If that function is also differentiable, then we can continue to take derivatives. We would call y double prime, or the second derivative of y with respect to x, is what we call our second derivative of y with respect to x. Now with the prime notation, we would put two primes on there to represent the second derivative. With the operator notation, we're using this exponent or the superscript of 2 to start to represent the second derivative. And the reason we have the 2 on the d part in the numerator is because it's the second derivative of our function y, but then in the denominator here we have the exponent on the x because it is with respect to x twice. So the first derivative was with respect to x as well as the second derivative. Now this process can continue. We could get the third derivative notated by either y triple prime or using the operator notation which says the third derivative of y with respect to x. Now once we start getting to the third derivative, this prime notation starts to get a little bit messy from here. So instead of writing y with 4 primes on there, or 5 primes, or 6 primes, this could get very cumbersome. Starting with the fourth derivative, we start to use the superscript notation. Now if we were to just write y to the fourth, that represents y to the fourth, not necessarily the fourth derivative, and we wouldn't be able to tell the difference. So notationally, we put the number of the derivatives in parentheses so that that is represented as a derivative and not a power instead. So in general, if I want the nth derivative, that would be y with a superscript of n in parentheses to represent the nth derivative, or in the operator notation, it would be the derivative, the nth derivative of y with respect to x all of those times. And the idea of the nth derivative here just represents any derivative that I could have, the first, the second, the third, maybe the 100th derivative, or the 13th derivative overall, but it is representing any nth derivative that I want to find. Let's look at a couple examples. So in this first example, we're asked to find the first 4 derivatives of this function y. Now, to get the first derivative, we could use the power rule on all of this, but to get to the second derivative, I actually will need the first derivative before I can move on to the second. So I can't go straight to like the fourth derivative, I've got to find them all in order since the next derivative is based off of the prior function. So for our first derivative, I'm going to use both notations in this problem. It would be y prime or dy over dx, and we're going to power rule this function. The derivative of x to the fifth would be 5x to the fourth. The derivative of negative 2x cubed would be negative 6x to the second. Since when we use the power rule, the 3 comes down, and 3 times 2 would give us the 6. Then we subtract 1 from the exponent. Plus, our derivative of 10x squared using the power rule would give us 20x. And then the derivative of 13x would give us plus 13. And then negative 4 at the end here is a constant, and the derivative of any constant would drop to 0. That would be our first derivative. Now, if we want to find the second derivative, I'm now going to differentiate the first derivative. Using prime notation, that would be y double prime, or using the operator notation, it's the second derivative of y with respect to x both times. And I'm going to just differentiate our y prime. So our derivative of 5x to the fourth would give us 20x to the third. Our derivative of 6x squared would give us 12x. And then the derivative of 20x would give us plus 20. And then the derivative of 13, now that 13 is the constant, would drop out to be 0. And that would be our second derivative. Now, we're asked to find the first 4, so let's find the third derivative next. So y triple prime, or using the operator notation, the third derivative of y with respect to x all 3 times. Now we can continue to use the power rule. So I'm looking at the second derivative and I'm going to power rule that derivative to get to the third. So the derivative of 20x cubed would give us 60x squared. The derivative of negative 12x would give us minus 12. And then 20 is now a constant, and derivative of any constant would drop to be 0. Now to get to our fourth derivative, the prime notation again becomes a little bit messy, so I'm using a 4 as a superscript, but I'm putting it in parentheses to represent that it is a derivative and not just a power there. So I have the fourth derivative, Or in the operator notation, I have the fourth derivative of y with respect to x all 4 times. And I can now find that derivative by differentiating our third derivative. So our third derivative here was 60x squared minus 12. The derivative of 60x squared using the power rule would give us 120x. And then the minus 12 is the constant now, so when we take the derivative of that, that drops to be 0. And those would be our first 4 derivatives. Now we could continue this process. I can't just stop at the fourth derivative. I could actually continue on. The fifth derivative would just give us 120. And then from there, the sixth derivative would actually start being 0. And any derivative past the sixth derivative is going to stay at 0 since the prior functions were just 0 themselves. And at that point, once I hit the fifth derivative, I no longer have a linear function like I do in the fourth derivative. I just have a constant of 120, and once I start differentiating constants, we are always going to pick up 0. Let's look at a couple other examples. So here in example 2, we're asked to specifically find the second derivative. So again, this y double prime would be the second derivative of this function f of x, which is 3x minus 16 all to the 5th power. Now, I'm not asked to find the first derivative, but in order to get to the second derivative, I actually need the first derivative first. So let's start by finding f prime. So our first derivative here of f of x, I'm going to actually need to use a chain rule. And the reason being is I have this inside function of 3x minus 16, and then this outer function of the 5th power. So in the chain rule, we start with the outsidemost function. Derivative of something to the 5th power would be 5 times that something all to the 4th. So we did the first part of the chain rule. We then keep the inside function the same. So 3x minus 16 stays the same. Times, we now take the derivative of the inside. Well, the inside function is 3x minus 16, and the derivative of that would give us 3. So our first derivative here would be 5 times 3x minus 16 to the 4th times 3. Now, to find the second derivative, I'm going to differentiate this function. It's actually helpful to do a little bit of condensing down when possible, and in this case, the 5 and the 3 are both coefficients, so I can multiply those to give me 15 times 3x minus 16 all to the 4th. And that's just helpful so I can start condensing stuff down and it doesn't look so cumbersome with all these parentheses of stuff getting multiplied. Now to get the second derivative, I'm going to differentiate the first derivative. So I'm no longer looking at the original function, I'm now looking at the 15 times 3x minus 16 all to the 4th. This again will still be a chain rule though because we have this inside function of 3x minus 16 to the 4th power. The 15 in front's a coefficient, so that's going to go along for the ride. You could product rule this, but since 15 being the first function is just a number, the derivative of that would be 0, so half the product rule would drop out anyway, so it's not necessary to use the product rule, but you could if you would want to. In this case, I'm going to start with the outside function, which would be the 4. The 4 will come down. 15 times 4 would give us 60, so I'm getting 60 as my coefficient there, of something all to now the 3rd power. Now in the chain rule, we keep the inside function the same, so 3x minus 16 stays the same, and to finish out the chain rule, I need to differentiate the inside function, and the derivative of 3x minus 16 would give us another 3. Now we could continue to kind of clean this up, especially if we were finding more derivatives after this, and 60 times 3 would give us 180 as our coefficient, and then we get 3x minus 16 all to the 3rd power. And that would be our second derivative. And the simplifying is definitely helpful if we want to find a third and then maybe a 4th or a 5th derivative from there. Okay, let's look at some more examples. So here in example 3, we're asked to find the second derivative of y with respect to x. This time we're given the operator notation as our question, but it is the same thing as f double prime. Our function this time is y equals x squared minus 7 all to the 4th power. Now to get to the second derivative, I definitely need my first derivative first. So let's start by finding dy over dx, our first derivative. What rules are we going to need to use in order to take the derivative of x squared minus 7 all to the 4th? So we're going to need a chain rule, and then we're also going to need a power rule. Our outermost function here would be the 4, so the 4 is going to come down. I'm going to get something now to the 3rd power by using that power rule. we keep the inside function the same, so the x squared minus 7 gets rewritten, times we now need to differentiate the inside function. Using the power rule, the derivative of x squared would give us 2x, and then the derivative of negative 7 would drop to be 0. So we have our chain rule here, bringing down the 4, keep the inside the same to the third, times the derivative of the inside. Now, like our last example, it would be helpful to kind of combine stuff that I could. Now, the x squared minus 7 all to the third, I can't multiply the 4 or the 2x into that because it's all being raised to the third first, and order of operations still applies, but I could multiply together the 4 and the 2x, and this would give us an 8x times the x squared minus 7 all to the third. Now that we have our first derivative, we can find our second derivative. So I'm going to notate that with the second derivative of y with respect to x both times, using our operator notation. I want you guys to think about what derivative rules we're going to need in order to differentiate this 8x times x squared minus 7 all to the third. So this time we're still going to need a chain rule, but we're actually first going to need a product rule. Now that we have an x in front, not just a number like we did in the prior example where we just had 15 here, but now that that is an 8 times x, that is one function, and then we're multiplying it to the second function, x squared minus 7 whole function cubed. So in this case, we actually first need to start with the product rule, and then when we differentiate the cubic piece, we will use the chain rule. So the product rule says we take the derivative of one function at a time. So the derivative of 8x would give us 8. I keep the other function the same, so I'm going to rewrite the x squared minus 7 cubed, plus I now keep that first function the same, so 8x would stay the same, times I now need to differentiate the second function. To take the derivative of the second function, we will need a chain rule. The 3 is our outermost function, so the 3 comes down. We then are going to keep the inside function the same, so x squared minus 7 stays the same. That's all now to the second power, since we subtracted 1 off using the power rule, times we need to take the derivative of the inside. Derivative of x squared would give us 2x, and then the derivative of 7 would drop to 0. So here again, I'm going to highlight these pieces. The 8 here was the derivative of 8x. We then kept the second function the same in the product rule, plus the 8x now stays the same, and then in these last parentheses is the derivative of the x squared minus 7 cubed. So we've got our f prime times g plus f times g prime. And then in addition to using the product rule, we also use the chain rule to differentiate that x squared minus 7 cubed. Now, if this were a multiple choice question, there's a little bit of simplification that we can do. In the first part of this sum, there's nothing I can combine there, so I'm going to just rewrite all of that. Oops, it is a minus 7 all to the third. But then for the second function, I actually have 8x times 3 times the 2x, so I could multiply the 8 times 3 times the 2 to get 48. And then I can multiply the x times the x to get x squared, and then rewrite that x squared minus 7 all to the second. And on a multiple choice question, if we're going to do a little bit of simplification, stuff like the 8x and the 3 and the 2, since they are not being raised to an additional power, can all get multiplied together to give us that 48x squared, and then keeping the x squared minus 7 squared the same. Let's look at one more example. So in this one, we want to find the first 3 derivatives of g of x, where g of x is 7x squared minus 2 over x to the 4th. So to get to even our second and our third derivative, I need to start with the first derivative. So I need to start by finding, I'll use for the prime notation, g prime of x. Now to differentiate the 7x squared, that's going to just require a power rule. So the 2 comes down, and I end up with 14x to the first. To differentiate the 2 over x to the 4th, I cannot power rule from the denominator, so I actually need to rewrite this function. So I'm going to just put an equal sign here because this is still the original function. I'm not going to take any derivatives, I'm just rewriting. To rewrite something where I have 2 over x to a power, I can bring that up to the numerator and make it 2 times x to the negative 4th by making the exponent negative using properties of exponents. Now to differentiate the negative 2x to the negative 4th, I can now use the power rule. So the negative 4 comes down, that would end up giving us a positive 8 since I have the double negative, and then we're going to get x to the negative fifth since we are subtracting off 1. Now, if this question just asked for the first derivative, we'd be done at this point. We do want to rewrite our answer without any negative exponents. So if I were to be stopping with just the first derivative, then I could rewrite it as 14x plus 8 over x to the fifth. But since we're asked for the first 3, I'm going to keep going. Let's find our second derivative. So the derivative of 14x would just give us 14. And then to differentiate the 8 over x to the fifth, I don't want to leave that in the denominator. I actually want to go back and use this kind of negative exponent unsimplified form of the 8x to the negative fifth. From here, we could power rule this. The negative 5 would come down, which would give us negative 40 then, x to the negative 6. And if I want to clean up and kind of rewrite that derivative, it would be 14 minus 40 over x to the positive 6 power. And that would be our kind of simplified form of our second derivative. Now from here, I want to get our third derivative, so I'm going to differentiate our second derivative. Starting with the 14, derivative of 14 would drop to be 0 since 14 is just a constant there. And then to differentiate the negative 40x to the negative 6, I can use the power rule again. The negative 6 would come down, that would leave us with positive 240, and then we get x to the negative 7th by subtracting off 1. And to rewrite this without any negative exponents, it'd be 240 all over the x to the 7th would be our third derivative. Now I want to point out some patterns that are happening here. When I just have polynomials, so I have x to positive powers, positive integer powers, I should say, I'm going to eventually start to drop off those functions depending on how many derivatives I'm taking overall. So for the 7x squared, that became a linear function of just 14x when we took the first derivative, and then that linear function became just a constant in the second derivative, and then once we hit the third derivative, that actually dropped to be 0, and any derivative higher would still stay at 0. Whereas when we have this 2 over x to the fourth, since that gets rewritten with the negative exponent, as we power rule, since we're always subtracting 1, that negative exponent is only going to become more negative, so I'm always going to have a derivative as I keep taking more and more derivatives. Whereas when I start with a positive integer value as my exponent, as I subtract off 1, at some point those exponents drop down to be 0. We also saw these two examples here between 2 and 3, where they both asked for a second derivative, but the subtle difference was what was the inside function. So on this first equation here, we had 3x minus 16, which is just linear. So when we took the derivative of the inside, we just got the number 3, which we can multiply to the 5 to get 15 there as a coefficient. That required that I just continue to chain rule it to take the second derivative. But in example 3 here, since I have a quadratic as my inside function here of x squared minus 7, when we differentiate that, we're actually getting a linear function of 2x. And in that case, in our first derivative, since we ended up with the 8x times the other function involving x, that then requires a product rule to take our second derivative. Now from the second derivative, if I wanted to find a third derivative, the first one here would just be a chain rule since I just have an 8 in front, but then the second function would require a product rule because of the 48x squared times the x squared minus 7 whole thing squared. So as we start to take more derivatives, sometimes we introduce new rules along the way. So in example 3 here, the first derivative was just a chain rule. And then the second derivative then required a product rule and a chain rule. And if we were to keep going, we're going to still have that product rule to deal with because of that 48x squared times that other function. So here's a couple examples just looking at different derivatives. And again, going back to some of that notation, we could continue to do this idea of taking derivatives as long as the functions themselves are differentiable. And the biggest thing to keep in mind is to get to any higher order derivative, you've got to start with the first derivative, then go to the second derivative and the third derivative and continue in order. Because the process of finding higher order derivatives just means that we're differentiating the prior derivative. So to get the second derivative, I took the derivative of the first derivative. To get the third derivative, I took the derivative of the second derivative, and so on as we continue through these.